So collision state theory discusses all of those things that I've kind of guided you towards, and just kind of been casually mentioning those factors that determine the rate of a reaction, things like the surface area and the concentration of the reactants and the temperature, and that's all that stuff that you've talked about when in grade 9 and 10, when you've ever talked about chemical reactions, what makes a reaction go quickly and what can slow a reaction down. So here's the things I want you to write. Just be careful here as you're writing. Write down, obviously, well, maybe not obviously, write down the yellow part and the examples, but don't write down the actual examples themselves. I don't believe they serve any purpose except to kind of guide you in some thinking as you're writing it down, all right? So factors that affect reaction rates, the nature of the chemical reactants. So that's one that's kind of the most abstract. What the reactants are actually made of obviously determines the reaction, the reaction rate. So I've got some fill in the blanks here just to kind of keep us occupied a little bit. And this is something that I've, taught you in grade 11, right? So if I've got copper and magnesium nitrate, no reaction takes place. You don't need to write that down. But if I have copper and silver nitrate, then I do get my single displacement reaction, and it happens very quickly. So you could say that the top one is like infinitely slow. It doesn't take place. The other one is very fast. Metals lower on the activity series are, can we figure that one out? What do I say about the metals on the activity series at the bottom? They want to be alone. So if they want to be alone, the metals themselves, how would you describe their reactivity if they want to sit there and be alone? What's that? Non-reactive, less reactive, all right? So we'll go with less reactive. Less reactive. So all those metals down at the bottom, they also tend to be found near the middle of the periodic table, right? There's our highly reactive metals. These guys in the middle, they are not very reactive at all. Actually, gold there is one of the least reactive. Platinum also very low reactivity. So some things are reactive, some things aren't. Another example of the nature of the chemical reactions of monatomic ions in aqueous solutions are very, and I don't think we might have some idea on this. We've seen some precipitation reactions. When we did our double displacement reactions, we would have taken our little eyedroppers and put a few drops of the silver ion, might have been silver nitrate, a few drops of the sodium chloride likely. And how long does it take for a precipitate to form when you mix those two reactants together? Anybody remember? You put them, one drop in, put the next drop. How long did it take for the precipitate to form? Anybody think back, that type of thing? It happens almost instantaneously. As soon as you mix those two reactants together, if they're going to form a precipitate, right away those ions bump into each other. They stick to each other to form ionic solids. And so reactions of monatomic ions are very fast. Okay? Precipitate formation takes place practically instantly. There would be some kind of measurable delay. Suppose if you had a high enough speed camera, you could maybe observe the precipitate kind of proliferating through the liquid, but it's pretty quick stuff. And if you think about it, I just have to have two particles run into each other. All they got to do is bump into each other, and we're going to have a chemical reaction. Reactions of molecular substances are often slow because bonds need to be broken and formed in the process. So there you can see I've already put in slow for you. So if you're dealing with larger molecules, we've got to break bonds, we've got to reorganize the atoms, we've got to make some bonds in order to form the products, and so that takes place slower than just a couple of ions bumping into each other and sticking together. Okay? So number one, the chemical nature of the reactants is a factor. And what I'm doing is I'm going through the chemical nature of, I'm going through the different factors, then we'll talk about what collision theory is, and we'll go back and we'll talk about how collisions can explain all this. Okay, factor number 2, 3, and 4. We'll put it all in one shot. And these are intuitive to you, more intuitive. Increasing the initial concentration of the reactants generally blanks the reaction rate. What happens if you put more concentrated stuff in there? What's it going to do to the rate of the reaction? Yeah, it's going to increase it. Temperature, also a very well-known one. Whether you've memorized it or perhaps you've had experience with it, maybe in cooking, that type of thing, because that's chemical reaction. Increasing the temperature, what does it do to the reaction rate? Yeah, it increases it. Uh-oh, did I get my A in there? Increases. What a mess. E's and A's everywhere. Jeepers. Rule of thumb. That just means kind of a general rule. It's not like it's absolute, but it's been determined that for almost any chemical reaction, if you increase the temperature by 10 degrees Celsius, you double the reaction rate. And that's an interesting kind of observation. Chemists had observed that when you increase the temperature 10 degrees, the reaction rate doubles, and it didn't matter what the chemical reaction was. And it didn't perfectly double. It was like approximately double. That's what a rule of thumb is. It's like an approximate rule. And that's interesting. That makes a comment on what we need to look at in order to study the reaction rate. Because if all chemical reactions double with an increase in 10 degrees Celsius, it must not be dependent on the reactant themselves. It must be dependent on something that's common to all chemical reactions. And that brings us to collision theory. It has to do with the collisions and how they're colliding that causes this. All right? And a catalyst. This is just a definition of a catalyst. Blanks the reaction rate without, and then I should maybe put a couple of blanks in that end one. What does it do to the reaction rate, a catalyst? Add a catalyst, what happens to the reaction rate? It increases it. It increases the reaction rate without. And then I put in there being consumed. You've learned that before. So I've got one blank. That's kind of mean, I guess. You need two. Without being consumed. Without being consumed. All right? And one more factor before we get into trying to explain these trends or these particular things, and that is the surface area. Increase the surface area of a reactant. How would we increase the surface area of a reactant? Yep. Yeah, make it into a powder, crush it. And what does that do to the reaction rate? Yep. Yeah, it increases it. Oops, my E's and S's are coming together. Increases the reaction rate. And a little statement there, the surface area affects heterogeneous reactions where we have something in the solid state and then something and then the other reactant in the aqueous or liquid or gaseous state. All right, but one of them has to be a solid so we can actually crush it up, change that thing. So there's a handful of little questions that that just deals with the factors I'm not going to have you work on them right now. What we want to do is continue on now with is discuss the collision theory itself and how we then can explain these things in terms of that. Okay, so that little initial note, I guess, kind of reminds us of the factors that we should be thinking of and how those factors affect rate. Now we want to talk about collision theory. We want to talk about what actually happens in order to initiate a chemical reaction. We're good to go? Some murmuring going on there. Now this note is obviously quite wordy, like compared to what we did yesterday, some calculations. But it is important. And these two bullets kind of summarize collision theory. I've tried to squeeze it down into the fewest words. For a chemical reaction to occur, the reacting particles must collide with each other. I don't think that's earth-shattering or groundbreaking. We talk about that a little bit in grade 11 when we talk about types of chemical reactions. I mention it one class. And we don't go into any more depth on it because we haven't talked about energy. It's all about energy of collisions and orientation of collisions right there. That's the whole thing. And not every collision is effective. Not every collision leads to a reaction. And so what we need to be able to understand by the end of today's lesson is what makes an effective collision. Got to have collision carts if I'm going to talk about collision. It's just a given. Okay, 2 requirements for an effective collision. I have no idea why I don't have just a period at the end of that statement. So in order to have an effective collision, and an effective collision is one that results in a chemical reaction. So now instead of thinking of a chemical reaction as a bunch of chemicals, I need you to think of a chemical reaction as, say, a couple of reactant molecules running into each other, and do they successfully result in producing some reactant molecules? Factors that determine this: they must collide with the proper geometry, all right? They must run into each other with the proper orientation that results in either bonds being broken or bonds being formed successfully. And they also must collide with sufficient energy, enough energy to break the bonds, all right? I can show you that very simplistically again with collision carts, all right? Collision carts tend to be, used in this orientation, in a very linear orientation, so that you can get a view of linear energy and momentum transfer. That's the way we use it in physics. You would never use collision carts like that. It doesn't really give you the same information that you got before. So that would be an indication of proper orientation, the way the collision carts aren't running into each other properly. In terms of proper energy, you can think of maybe, my collision carts running into each other, and here I've got a little hook on the side just for the, for the purpose of just, demonstrating. But you could imagine then that the purpose of this collision was to bring that plunger in close enough so that my little hook has to kind of hook into that hole there and have them stick together like that. See, isn't that cool? See? A little rudimentary, but I think you get the idea. And so let's imagine then that in this particular reaction, this cart has to collide hard enough to squeeze that plunger in order for that latch to be hooked on. So if I give it just a little wimpy push, there's no way that plunger is going to get squeezed hard enough in order for that successful linking of the two particles. You could think of it like two hydrogen atoms trying to come together to form a hydrogen molecule. And if they don't run into each other with great enough energy, then that link isn't going to be formed, all right? Now, even though this is a silly little simplistic demonstration, it does illustrate all of the important things. In our next slides, we're going to start talking about what kind of energy does it need. Well, what kind of energy does this first cart need in order to successfully have that plunger get squished? What do we call that energy when I give that thing a push and let it go? What do we call that type of energy rolling along there? Yep. Yeah, and that's exactly the same for a molecular situation. A molecule has to have kinetic energy in order to initiate a chemical reaction. So that kinetic energy has to be sufficient. And ultimately, where does the kinetic energy go in this case when the plunger is squished? What do we call this energy when we take a spring or an elastic band and we cause it to deflect like that? What do we call that stuff? Yeah, in this case, it's elastic potential. You're right. I'm looking for just potential in general, but you're right. In this case, it's elastic potential. And that's the same thing with our chemical reaction. In order for two molecules to come together, or two atoms, they have electron clouds that are repelling each other away, right? Two clouds of electrons come together, they push on each other, they push each other back. So instead of having to overcome elastic potential energy, they have to overcome electrostatic. Remember our electrostatic energy from, not energy, but force from last year? They have to overcome that electrostatic force of repulsion in such a way that they get close enough together that they can form that bond, all right? So we've got kinetic energy going into potential energy, and if we've got enough of it, we can store it in a new bond being formed, all right? Okay, so let's talk about a couple of terms here that we're going to be using in order to describe this stuff. And these two terms are exactly what I've described. They're the kinetic energy and they're the potential energy, but in the chemistry world, we've given them other titles. We've just given them some new names just to mess you up. Actually, it's not too bad. I guess in chemistry what we like to do is when we define things, we like to define things in terms of the minimum energy needed. All right, I guess in physics, we just talk about kinetic energy and potential energy, and you can have all kinds of different values of it. What we're doing here is we're taking that kinetic energy and potential energy and we're saying, let's define the absolute minimum amount needed to successfully do what we want it to do. That's what these definitions are. So I've got a cart moving here. It runs into the other cart. If it's going fast enough that it'll successfully couple these two carts, then I would say it has the threshold energy. It has the minimum amount of kinetic energy needed to successfully make that happen. And you'll notice that in threshold energy, it talks about the kinetic energy needed. Activation energy. It's the minimum amount of potential energy that's required to cause the reactants to change. It's actually the same energy, except it looks at it from a different point of view. If I switch my carts back around here, so I've got my little cookie thing on the back end, same idea. I've got to give it a push such that it, can squish that spring and latch onto it. I even wrote EA on this bar here to put my point across last time I did this demonstration. From the point of view of the moving particle, the threshold energy is the amount of kinetic energy that this thing has just before it runs into it. If the threshold energy is the threshold energy must be equal to the energy of activation. The energy of activation is from the point of view of the potential energy needed to successfully have the reaction happen. The potential energy needed just to make that couple together is what we would call the activation energy. The threshold energy simply looks at it from the point of view of the kinetic energy, the moving thing, and the activation energy looks at it from the point of view of the potential energy that's needed to make it happen. So really, they are the same amounts of energy. They're just looking at them from a different point of view. Let me give you a little analogy. You can think of all of this also not just in terms of carts, but in terms of maybe taking a ball and rolling it up over a hill. All right? Let's say that we're playing some kind of carnival game where you've got to roll the ball up the ramp and into some kind of a thing, right? And you're getting ready to roll the ball, you give it a push, and you give that ball some kinetic energy, okay? And the ball rolls up the hill. If you're wimpy, like myself, my wife says I throw like a girl. That's okay, she throws like a guy, so it's just as equal. Anyway, she can also outdrive a golf ball than me. It's sad. It really is. Anyway, so if you're like me, little granny throw. And it doesn't make it up the hill, it's a failed rolling the ball over the hill, if that's what your purpose in life is. In other words, you didn't give it enough energy. But if you roll it with just enough threshold energy, in other words, if EK is equal to what we call ET, just enough, then what's going to happen is that ball is going to roll up the hill and it's just going to make it over the top. Just. Perfect. You've rolled it just up the hill and it just makes it over the top. It's like, is it going to make it? Oh, it's right at the threshold. Oh, made it over the top. All right? I'm right to the pinnacle of... Welcome.
Welcome. Oh, I was just talking about that this morning at the breakfast table. If you handle like that.
So, we've successfully just rolled the ball over the hill. Activation energy looks at it from the point of view of the potential energy. So instead of looking at it from the point of view of the rolling ball, if we were to make a measurement and determine how much potential energy is needed to get the ball over the hill, then we would call that the activation energy, all right? And the amount of energy needed to just roll it over the hill in terms of potential energy is the amount of energy you need to put into it in terms of kinetic energy. So they mean the same thing, we're just looking at it from a different point of view. One's from the potential energy, and one is from the kinetic energy that it has, okay? And you can think of the ball rolling over the hill as being a successful chemical reaction, all right? So that's in terms of energy. So now we've got proper orientation and proper energy. Those are the two things we need. So then, let's then define an effective collision. An effective collision is when the reacting particles collide with a proper collision geometry and the sufficient energy in order to break the bonds and form new bonds. I guess I could take my analogy of rolling the ball over the hill and add an orientation component by, instead of rolling a ball, I have to roll a cylinder over a hill, right? If I attempt to roll the cylinder end over end, right, this orientation, that's definitely not going to get over the hill, right? But if I attempt to roll that cylinder, right, in the orientation that it's going to roll, then I have the opportunity to get it over the hill by rolling. So if I take my ball and change it into a cylinder, then I've got a complete analogy. An ineffective collision is where the reacting particles rebound unchanged from the collision due to either improper collision geometry or not enough energy. It's one of those and/or scenarios. You need both requirements to have a successful collision, but if only one requirement is not achieved, unsuccessful chemical reaction. You might even get the impression, man, if it's so easy to have an unsuccessful collision because of either lack of energy or lack of orientation, wow, it's amazing that any chemical reactions take place at all. And I guess that's what we want to discuss. What then makes those reactions that do happen so easily, what makes them so effective? And I'm sure you've encountered times where you can't get a chemical reaction to go. Think about lighting a campfire. If you've ever gone camping, sometimes it doesn't matter what you do, it's just not going to work for you. You end up out of matches. What's going on? Why can't I get this to react? It should be an easy chemical reaction. But if the wood is damp, then you can't get the particles going fast enough. You can't get enough energy into them. They're fairly complex molecules. You can't control the collision orientation. So sometimes you do struggle with a chemical reaction. Okay, so in order to have a reaction, we need proper energy. Things have to be going fast enough, and we need proper orientation. Okay? And if one of those fails, unsuccessful chemical reaction, the particles just bounce off of each other like billiard balls, and they go on their way unchanged. Yeah, this is a wordy note. There's no other way about it. If you're murmuring back there, it's just the way it is. It's just the way it is. I deleted an orientation slide. Where did that slide go? Oh, rats. I wanted to give you an example of good orientation versus poor orientation. I had a blank slide and I drove right past it. But I can come back and talk about good and poor orientation when we're done talking about energy. We'll just do it on the flip side. We'll just talk about what makes, how we analyze whether there's good enough energy or not, and then we'll talk about the orientation. We'll double back. It's not a big deal. So we still need to discuss examples of good orientation. But for now, we'll talk about energy. Collision energy depends on the kinetic energy of the colliding particles, all right? And that I don't think is too surprising. We've talked about some analogies here. We know from past discussions, courses, temperature is a measure of the average kinetic energy of the particles. The higher the temperature, the higher the kinetic energy. And so there's our relationship. You heat something up, the particles move faster. If the orientation is correct and the energy is correct, successful collision. We want to look a little more closely on how the temperature affects the energy in the particles. And what we use here is something called a Maxwell-Boltzmann distribution curve, which describes the relationship between kinetic energy and the number of particles in a system. And I have these graphs here so that you don't have to write down these graphs and you can just put notes on them. Two, three. Let me just bump that thing too. Okay. I've probably mentioned the name Maxwell Boltzmann earlier on when we talked about thermodynamics. In the mid-1800s, these gentlemen attempted to explain what we call the kinetic molecular theory, which states that particles move and vibrate in substances, and if the temperature increases, the particles move faster. And not only did they make statements like that in lots of equations, but they created graphs that successfully map out the distribution of particles in a sample of substances. All right. So let me carefully describe to you what is happening on these graphs, because on the test, I do like to make you sketch graphs like this for understanding. So here's what we have in this particular graph. Let me grab a dark thing. So number of particles, all right? So this is the number of atoms or molecules or whatever, particles, entities. It doesn't make any difference. And this is graphed versus kinetic energy, okay? So way out here, we've got the particles that have really high kinetic energy. So these particles, they're moving. They're zinging like crazy. They're bouncing around at like top speed. And then we also have a very few particles that have very low kinetic energies, all right? They're moving very slowly in a sample of gases. They're hardly moving. So we've got some super fast movers, and we've got some slow movers. So what this really is a snapshot of everybody's speeds in the sample of a gas or of an aqueous solution. And you'll notice in the middle there's this big bump. And so there's this large number of particles that are kind of going medium speed, all right? So you got some speeders, you got some grannies, right, some slow movers, and then you've got a big bulk of them going the medium speed, all right? The area underneath this curve represents like the total number of movers, the total number of particles. So if we were to take all of these areas under here, we would then kind of determine, we would have the total number of all of those particles that are moving around, all right? So if we then have this kinetic energy and this minimum kinetic energy needed to react, in other words, all of these particles over here to the right are balls or cylinders that have a big enough push to make it over the hill, then this shaded area here represents successful chemical reactions if the orientation is correct. If the orientation is correct, these guys here have enough energy to make it over the hill and a reaction happens. Okay? So this is simply a chart of kinetic energy versus the number of particles. This analogy is really a terrible one because it doesn't have to do necessarily with kinetic energy. But I like to imagine it like making popcorn, where it really doesn't have anything to do with kinetic energy but number of particles. When you start to make popcorn, it starts off slow, right? There's an odd little popcorn pop, 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 pop. And then when you get to the middle, you got all kinds of them. Pop, 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 it's popping like crazy. And then when you get to the end, there's, you know, the odd straggler, pop, 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 dying away. So I like to think of that curve, you know, in the same way as the numbers of popcorn kind of popping. That has nothing to do with kinetic energy. It has to do with time versus heating the popcorn. But I can at least get a visual representation in my mind because I can kind of hear that popcorn in my mind of the slow movers and then this big kind of glut of medium speed movers and then these super fast movers on the end, being a distribution. Okay? What I want to talk about next is what happens to this curve when I change the temperature, if I increase the temperature. So the next picture, you'll see, I'm hoping this is the next picture. Next picture. I've added a new curve, okay? And it represents a temperature that is a little higher than my last one. So you'll notice I've got this in blue to be cool. It's the cool temperature, and then I've heated it up. For every possible temperature, there is a different Maxwell-Boltzmann curve because the equation gives you a new curve. Let's take a look at the properties of the curve that have changed because of the temperature change. Notice, number one, the entire curve has shifted to higher kinetic energy. That makes sense. It's hotter. Everything's going to be moving a little faster. Number two, notice that the peak has also shifted to the right. That indicates, again, that it's hotter. Also notice that the peak has come down very slightly. And that's because if I'm going to have more particles spread out down here, then I have to have less particles at the cooler temperature. I like to think of the Boltzmann's curve for a hotter temperature as if you took the cool one like a string and you pulled it, and it kind of took the string and pulled it down and pulled it over to the right, right? As if it kind of took that constant length of a string and just kind of pulled it down and moved it to the right, okay? Like I said, I often like to get you to sketch these curves, and so I want you to be able to be aware of these differences in the curves, okay? All right? And Jenna's just dying to keep her eyes open, but I'm going to have a movie on it. She can watch it tonight when she's wide awake. Let's notice what happens here as I heat it up. So we heat it up, the graph gets kind of pulled, the peak comes down. There's my threshold energy. That energy hasn't changed. That's the energy needed for a successful collision. Now notice, though, there's a larger area because my red line is above my blue line. At higher temperatures, there are more particles that now have enough energy to make it over the hill and therefore the reaction rate increases. Because I now simply have more particles going faster. Okay? So as it gets warmer, the threshold energy stays constant. That's the energy needed for the reaction to happen. That's a fundamental part of the reaction. But as it gets warmer, it pulls that line to the right. It brings that line. It doesn't bring it up. It's kind of like pulling it out there, and it kind of stretches it out, and you have more particles going at the right speed. It turns out that that area that is past the threshold doubles, approximately doubles, every time the temperature changes by 10 degrees. There's where the rule of thumb comes from. It comes from how this graph changes every time you increase the temperature by 10 degrees. When you increase the temperature by 10 degrees, this area past an arbitrary line tends to double. That's where that rule of thumb comes from. At this point, the chemical reaction is slow. But if that temperature increases to the point where the big hump in the curve gets past the threshold energy, then you've got the majority of your particles that are able to react, and the reaction goes like crazy. Produces lots of whatever, gas or product, whatever it is. Okay? You can have a reaction where the threshold energy is really low because different chemical reactions, nature of chemical substances, if the threshold energy was down here, that reaction is going to go like crazy. Most of the particles have enough energy to react. The reaction happens fast. Okay? All right. So two observations that are apparent from this graph. What is that last graph? Oh, the last graph is for a catalyst, and we'll talk about that a little bit later. So just kind of leave that paper aside. Or you can write this beside the graph. Yeah, that's a great place to put it. But the last graph is a catalyst graph. I'll come back to that in a moment. Two things apparent. At both temperatures, a relatively small number of particles will collide with enough kinetic energy to overcome the EA barrier. And as the temperature increases, the fraction of particles with enough EK to react increases. The higher the temperature, the faster they're moving, the more successful collisions from an energy point of view. Now, I said that I kind of missed an opportunity to discuss what a good orientation is, and I said I was going to go back and write it down, but you know what? Nothing needs to be written down in terms of good orientation. All I was going to do is discuss a couple of examples of where orientation is very important. I'm going to just quickly do this on the board for a moment. A chemical example, and I learned this one in university, is if you have something like hydrogen, hydrogen, hydrogen with a bromine, all right, stuck to a carbon. And we will learn in the structure and properties note that particular molecule has a shape like this, all right? It's a tetrahedron. And one of these being a bromine. And I learned in a lesson in university that the only way that the reaction between, say, an iodine and this particular molecule was to have this molecule run into the back of that molecule from that direction. It's the only way it works. Because what happens is, as the iodine comes in, it pushes the H's up till they're like flat. And then it actually flips the H's over and ejects the bromine from it. So the iodine then forms a bond on the back end, and this bond is broke. You're left with an I sitting out here, and it's probably only got 7 electrons. You've then got the carbon with the 3 hydrogens and the other iodine that has formed the bond. And then you've got this Br that's sitting out here also with 7 electrons, and those two could get together. And anyway, the important thing is that this reaction could only happen if the iodine not attacked, well, we say attacked, even though it doesn't have brains, it's not attacking it, but bumped into that molecule on the back end side of the bromine. If the iodine runs in on the bromine side, bounces off. Unsuccessful reaction. All right? So there are many examples of reactions that we could talk about that have an orientation situation, but I'm not worried about that. You know this, but there's an example of an orientation. All right? So orientation and proper energy are the musts that we need to overcome in order to have a reaction. Okay, so now, we're coming to the end. Okay, no, who's kidding who? There's about 20 minutes left. But what I want to do now is, I want to go back to all of those factors that affect reaction rate, and I want to talk about them now. Oh, and I've got a frozen slide. You guys are staring at me like I'm crazy, and I am. Anyway, what I want to do now is go back and look at those factors, but we now want to discuss them in terms of proper energy and orientation in order to explain why those factors change. So this explanation, and you will have to do explanations like this on a test, right? Well, I'm not going to teach it to you. You're not going to put it on a test. Like, really? Come on. These explanations are a little bit like when I taught you last year about number of orbits and number of protons, right? You always had the 2 arguments. Same thing here. If we're looking at how temperature affects a reaction rate, that's just an example. You're going to think, what does it do to the frequency of collisions? And what does it do to the fraction of effective collisions? So you're always going to argue those 2 points. Sometimes only one of those factors will be affected. Then that's the only one you argue. Sometimes both of the factors are affected. Then you will argue that as well. So you're thinking about those 2 factors when going through any of these arguments. Anytime you want to explain why a reaction gets faster or slower, doesn't matter, you're thinking of these 2 things. Now, up to this point, I've only talked about 2. The fraction of effective collisions. Did it orient itself right, and does it have enough energy? I've put those 2 into this 1. Frequency of collisions is just how many times do the particles bump up against each other per second. And that is totally temperature dependent. If you change the temperature, you change how many times the particles bump into each other. All right? Actually, that's not true either. It could also be concentration dependent. You put more of the particles in there, they're going to bump into each other more often. So, frequency of collisions, you need to think, how many times are the particles going to bump into each other? Fraction of effective collisions, that's how many of those collisions have good orientation and good energy. That's what it's all about. So all we have to do is apply those 2 things to each of our different factors. Okay. Don't write, obviously, the little box up here. That's just to keep that fresh in our minds on the screen. Concentration. And I'm not doing this in order in which I presented it last time, and that's because this is a good logical order in order to cover it. And those two pictures on the bottom used to be animations, but with the upgrade in the PowerPoint, it won't run my animations anymore. And the difference in these pictures are just 2 reacting particles versus 4. Increasing the concentration increases the number of reacting particles. If there's more reacting particles, then therefore the frequency of collisions increases. It's increased that number of collisions per second. If there's more collisions happening, then there's a greater probability of having those successful collisions. The reaction rate increases. So simply by having a greater concentration, you have more particles colliding. And by having more collisions, that fraction of good ones will take place more frequently because they're just happening faster. So concentration is dependent on, number one, in terms of explaining it. There's just more collisions happening, and therefore you're going to have more frequently successful collisions, more reactions. Number 2, surface area. Surface area is the same thing. If you've got a solid and it can be broken into many chunks, then again, you're going to have more collisions taking place on the surface. Again, my animation was of a nail that was rusting, and then in the next part of the animation, the nail broke into pieces, and every time there was a collision, you could see that there was a reaction. So this increased, again, the frequency of collisions. So surface area is really like concentration. You're opening up reaction sites or sites for collision. So again, the argument is the same. There's more sites for collision, therefore the frequency of collisions increases, and it happens faster. So surface area, very much like concentration, factor 1 is what's being affected. Okay? Again, there's just a little representation. If you've got it in a large cube, you can only have collisions with the surface. You break it into smaller pieces, you can have collisions all over those surfaces, increasing the rate of collisions. Temperature effect. The temperature affects both of our factors. Again, I've got animations, and these animations that aren't working, same number of particles, but one goes faster than the other. I don't think it takes too much, imagination to realize that if you've got particles moving faster, number one, they're going to run into each other more frequently. So you're going to have more collisions. And we just saw on our Maxwell-Boltzmann distribution curve, you also have more kinetic energy in each of the particles, and therefore you have changed the fraction of effective collisions. You've changed both factors. So not only are they running into each other more often, they're running into each other more effectively. If you think about concentration and surface area, you haven't changed the temperature, so they're not going any faster. You're not making them more effective collisions. You're just having more collisions. That still increases it, but it doesn't change that second factor. You're not changing the kinetic energy with which it's colliding. So temperature, you can argue both. Okay? What are we down to? Nature of the reactant, I think. By changing the type of reaction or reactants and not changing the temperature, if you haven't changed the temperature, you're not making them go fast enough. You're not changing the frequency in which they collide. But you change the effective collisions. Number two. Really, when you change the reactants, you're changing that activation energy. You're changing that threshold energy. You're changing the height of the hill. They're not going any faster, but the hill just got lower. You're going to have more of those particles making it over to the successful reaction side. And depending on the type of particles we're dealing with, it may just mean weaker bonds, lower the activation energy, or it could be complicated molecules needing a better geometry. So it could be the energy and geometry effect. Might just be the energy effect. If we're dealing with something like a single displacement reaction, geometry really isn't that important. They're ions. They're very simple. So if you change the reactant from copper to zinc, you're probably just changing the activation energy requirement. But if you're dealing with large molecules like biological molecules, then there's also an orientation effect. And I'm pretty sure the last factor we're dealing with is the catalyst. How does the catalyst increase that reaction rate? And we're getting there. I know it's been long and painful. This is the type of lesson that there will be homework questions for understanding, but what you want to do tonight is read through those notes and maybe distill out the most important parts, right? Proper energy, activation energy, threshold energy, and proper orientation. And then go back and look at these and think about those factors, right? So the last one here is the catalyst. So a catalyst kind of cheats the system. A catalyst almost appears to be some kind of magical substance that just all of a sudden makes that reaction spontaneously go faster. You haven't heated it, haven't changed the nature of the chemical reaction, the reactant. So you'd think it should sit there just like it did if it was going slowly, but then you add the catalyst and it reacts like crazy. So the catalyst then provides the reaction with an alternative pathway that has a lower activation energy. It's like if we're talking about rolling the ball over the hill, it's like it cheats and burrows a hole into the side of the hill so that the ball doesn't have to actually go over the hill. It makes it energetically easier for the particles to make it to the successful reaction side. Almost like a cheat. So right away, without having to change the temperature, there's more effective collisions because they can go through the shortcut. And my next slide is now that last graph on that handout I gave you, which should show you that with the catalyst, the threshold energy has been shifted to lower kinetic energies. Again, like I said, it's like we take the big bump out of the hill so it can like cut across easier. So I think everybody has it. I'm just noting here. So here we've got the uncatalyzed line from in our first one. That's how many are going to react at, without a catalyst. And by adding the catalyst, it cuts off the energy needed. And so now I've got this larger area. It's not just this area in here, but it's the whole area that now has the ability to react because it doesn't need as much energy to get over the hill. And so now a lot more can react, right? Now all these extras have enough energy to react as well. Okay, so the catalyst shifts that threshold energy needed. Okay? Yeah, and I've changed these here. This says threshold energy catalyzed, threshold energy uncatalyzed. Yours says under here, right, the new activation energy. I like the term threshold energy there. I'm not that picky on it. If you were labeling it, say you called it an activation energy, if we were doing it on a test, not a big deal, but I like that way a little better because it's a kinetic energy. Okay? All right. So it does a little bit of a cheat. Yeah, there's nothing important there on that one. This was an animation. Again, it's not functioning. And there is some practice problems to just talk about. And again, it's just talking about what happens if, and if you change this, and what happens. And again, your arguments will always be, what does it do to the frequency of the collisions, the change, whatever they're suggesting, and what does it do to the number of effective collisions? All right? Frequency is how many times the particles run into each other, and the effective collisions are, does it have enough energy, and is it in the right orientation?